again, guys. This morning I'm going to go through the basic workings of a 3-wire circuit. This is not in your worksheets, and just to let you know, later after this video thing this morning, I'm going to be downloading some more worksheets to do. So my plan is right now I'm going to go over the fundamental workings of a 3-wire. I'm going to go over 2 problems in the worksheets over here, and then I'm going to shut her down. I'll download some more worksheets, and I'll give you the weekend to work on them. Monday, we'll answer any questions with 3-wire because it's very crucial we get this 3-wire. And then Tuesday, I want to have the test, and it'll be a Moodle test. It's already built. It'll be ready for us. And what I'm going to do is I'm going to open it up for a specific amount of hours, and I'm going to give, once you log on, whatever time works best for you, then you're going to have 2 hours to finish your test. All right? So let's start with a 3-wire. This is a basic Edison 3-wire. By the way, I can't prove this, but I think that bastard stole it, right? So here we go. This is a typical house. 14.9 is distribution, 14,900 volts. And it's primary here with a neutral. That's the lower wire. When you got 2 wires coming in, you see on your sparrow wire. Now, and this is a typical transformer that's hanging on a pole outside a house. This is also the transformer that sits in pads for underground distribution, except we run underground to it. It's a little bigger. Now, so we got 14.9, and then we've got 240 volts right here, and they take the center point on this coil and they ground it. So they ground it and they ground it. The definition of a neutral conductor is that it packs current at earth potential. So your neutral conductor packs current at earth potential. It can never have a switch in it. It can never have nothing like that. And the way we talk about an Edison 3-wire, for this one, for example, let's just say, a saying we have a lot of times is a balanced 3-wire. So if ignore these ohmic values over here, if I'm drawing 10 amps with this one, and 10 amps with this one, 10 amps comes through here and goes home. No current on the neutral in a balanced 3-wire. A balanced 3-wire where we've got 2 equal loads, you could remove the neutral and you wouldn't know. And it would run 220 volt things perfectly off 240 volts because we get an equal voltage drop on each one. Now the neutral is there to hold it steady if it's not balanced. And the case where it's not balanced is, let's go like this. Let's say this is 10 amps and this is 5 amps, okay? So in that case, let's follow this, and even though in AC and transformers, this changes from negative to positive 60 times a cycle. And we'll do that with second year. We don't have to worry about that. I give these for first year, guys. I give these a polarity. Negative, positive. Here's the trick to the neutral. This neutral here is positive with respect to L1, but it's negative with respect to L2. Okay? That's the Edison 3-wire. At any one, it even happens, but it changes quite a bit in AC. So here we got 10 amps coming this way. Comes down, does 10 amps worth of work in load 1. We come into this node 10 amps. 5 of the 10 amps goes down this way and comes here. 5 amps, 10 amps. Now, we got an extra 5 amps, and it's going to go this way. On the neutral, because when we get into more complicated neutrals, and we will be doing that today, what you do is you figure out your line 1, line 2 amps, you go like this, 5 amps, 10 amps, that the difference is on the neutral, which is 5 amps, going the same direction as the smallest amps. So whatever these numbers are, like this could be 30, this could be 2, so it'll be the difference, right? 28 amps going in the same direction as the smallest amps, because everything's got to go to and go home, all the way from the WAC Bennett Dam. That's the way it works. All right? So in this case, let's get rid of this one here, and let's just work this one really with the ohmic value I've got right here. Okay? So I've said that I've got a 5 ohm load and a 25 ohm load. Okay? So I've got 120 volts on this load. If I take my voltmeter across here, I've got 120 volts there. 120 volts divided by 5. My calculator guys aren't working so well.
25.6.
25. No, it's not.
Yeah. 120, what is it, 120 divided by what?
5.
24.
24 amps, okay? So that's 24 amps in this load, which is a true statement. What's in this load? 25 ohms, 120 divided by 25.
4.8.
4.8 amps. So look at this. Let's carry this down with this polarity right here, you guys. This is 4.8 amps going home. Going out, I've got 24 amps. So I do this. 24, 4.8, what's the difference?
19.2.
19.2 amps on my neutral, going in the direction of the smallest line. Going this way, okay? Done. So that's the neutral. Now, let's take this same neutral, this one right here, and let's say we get a first year guy that's dumbered in a sack of sledgehammer handles, and let's break this neutral. If he opened up that neutral right there. Now, when we're doing this, everything changes. The only thing that doesn't change, you guys, and I've said this 1,000 times, is the actual resistance of the load. That 5 ohms and that 25 ohms is a physical characteristics of the load that it's designed, right? So now, instead of having 120 here and 120 there, I've got 240 over this. So now let's look at this. 240 volts divided by total resistance, which is 5, and 25, which is 30, which would cause 4 amps to flow, right?
240?
240, no, yeah, sorry, I was dividing it by 120. Okay, 240 divided by 30 is what?
8.
8 amps. We get 8 amps going in there like this. And it trucks through here, 8 amps sails across a 5 ohm resistor. Now, the lower the resistor, the higher the current draw. The lower the resistance, the higher the current draw. You can think of this as a range, and we can think of this as a microwave, you know, because a microwave has a fairly high resistance. Now, so what's my voltage drop on this 120 volt rated load? 8 times 5.
40.
40 volts. Okay? So we come down here and 8 goes over 25. What's my voltage there?
8 times 25 is 200.
200 volts. Now, this is what happens, you guys. If you ever walk into a house where the neutral's been broke, and for example, I'll tell you a story, when they were wiring up the casino out there, there's a subdivision right behind the casino. I forget the name of the subdivision. But anyway, a backhoe operator knocked a tree, knocked the neutral, broke the whole neutral to that entire subdivision. Everybody in that subdivision lost their microwaves, their transformer on their furnace, any high resistive device, stereo components, because then you get huge voltage drop over high resistance devices, and you get no voltage drops over your stove, your baseboard heater, your hair dryer. They don't care because they're low resistance, high elements. So that's why and that also explains why we never switch or fuse the neutral. The only time you're allowed to switch or fuse the neutral is if I had a 3-pole switch and it shut them all off at once. And usually that's in a generator situation. All right? So that's the basic workings of a 3-wire system. Okay? Now we're going to swing over here. We're going to solve